перетворилася наша конференція. Тобто на тому знімку, що от був наш чер представлений, там не можна побачити, що в тому Royal Holloway також є червоний корпус, а от на цьому маленькому малюночку то можна побачити. Він так і називається Red Building. Тобто є от, ну, я тут представляю оцей університет в Лондоні, де з червня працюю, і звідси з Лондону керує своїм департаментом Cyber Security в Інституті телекомунікацій та глобального інформаційного простору. Тобто таке зовнішнє керування онлайн, і займаємося практичними речами, там цікаві люди, можна на веб-сторінки побачити, у мене задіяні. Ну і оця доповідь, вона підтримана фаундейшн таким, це називається British Academy, нагорода British Academy для дослідників під риском, бо на нас були кібератаки, і вони запропонували свої знаряддя, свої комп'ютери, і тобто така трошки історія. І є спільна програма між Royal Holloway та Інститутом телекомунікацій, тобто от працюємо там. Ну, я вже казав, що наш цього університету замдиректор Олексій Лебідь, абсолвент Мех-Мату, вчора отримав диплом доктора наук, і якраз він займається оборонною тематикою. Тобто, ну, а про чисту математику, тобто відокремлю все і більше сконцентрую на алгебраїчній геометрії, навіть скінченні графи буду оминати. Слайди у мене англійською, є слухачі, для яких англійська більш природна, то я перейду на англійську. Тобто, simple graphs without special cycles. That's the topic. I have three items. First one, classical extremal graph theory, developed by Paul Erdős and his school. That it has been started with the following problem formulated by Hungarian mathematician Turan. What is the maximal value, xvc2n, for the size number of edges, that size, of graph on V vertices without cycles c2n of length 2n? And other question, I think it belongs to Erdős, is about maximal size xv, c3, c4, c2n, c2n plus 1. So this maximal size of the graph which has no cycles, c3, c4, c2n, c2n plus 1. It means that the girth of this graph, investigated graph, has to be bigger or equal than 2n plus 2, because girth is just the length of minimal sample graph. Recall that here it's written, and according to Erdős even circuit theorem, size this xvc2n is O large v1 plus 1 divided by n. So it's not for this graph, it's not if we have number of vertices to n, it's not something n square, but a kind of sublinear interesting bound. It's so-called Erdős even circuit theorem. In fact, Erdős never proved it, but a crowd of people with Erdős number 1, his students, proved it later. No, because here you see O large, it's in fact upper bound. because all lunches means exists the constant C that we have less or equal C times V 1 plus 1 divided by N. But lower bounds from other sides, it's very interesting questions about this XV C to N and XV C3, C4, C to N, C to N plus 1. That is important direction of extremal theory. The subitem, that's one piece of mathematical classical extremal graph theory. Second one, classical object, geometrical objects of algebraic geometry are algebraic graphs, i.e. simple graphs or graphs of binary relation defined over algebraic varieties over field F, such that the edges are also algebraic varieties over F. Some remark that algebraic graph means that set of vertices supposed to be algebraic variety in the with the risky topology, and a set of edges as well has to be algebraic variety. Okay, studies of algebraic graphs with prescribed girth and diameter form classical direction of geometry. I just recall that what is the classical projective plane. So kids defined a projective plane as a graph over arbitrary field, or even some classical construction of projective planes. In fact, they are graphs of girth 6, so minimal cycle has length 6 and diameter 3. It's equivalent. We have one edge through 2 points, and 2 lines are intersecting in 1 points. So it's in fact, in classical case, disjoint union of 1-dimensional and 2-dimensional vector spaces of F cube. So 3-dimensional vector space, we have projective points, dimension 1, and projective lines, dimension. Okay, so kids who got the Abel Prize in 2008, famous mathematician, defined generalized M-gon as a bipartite graph of M and diameter M. So diameter, it's clear, that's maximal distance between 2 vertices within the graph. And noteworthy the geometries of Chevalier groups A to F, simple groups, B to F, Dynkin diagram A2, B2, and G to F are generalized M-gons for M equals 3, 4, and 6. So that, and studies of families GIF of homogeneous algebraic graphs defined over the field F with well-defined projective limits when the n tends to infinity form an interesting direction of algebraic geometry as well. What means that homogeneous algebraic graph? It means that if we consider neighborhoods of vertices, say it's supposed to be isomorphic or alternative definition, at least they have of the same dimension, and we can consider infinite graphs which can be obtained as projective limits of GIF. What means projective limits? It means that we have a family GIF, and from GI plus 1 F to GIF, there is some canonical homomorphism, and this way we get projective limit. So that here I described already what means homogeneous, that stable dimension of neighborhood of vertices, dimension K, for instance, homogeneous or K homogeneous. And of course, one is interesting case when we the projective limit of algebraic graphs is a tree or a forest. That is interesting. So if we have such situation, we can talk about forest approximation over even we can change the field for commutative ring K. Okay, so what we can talk about such families which form with well-defined projective limit. Interesting case if Gir's GI of each graph GI is bigger or equal than some independent constant C times Ni, that where Ni is dimension of the vertex set of graph VGI. In this case, we can talk about algebraic forest approximation, that we approximate the forest infinite graph by finite graph GI of large Gers, because this condition is classical condition of in simple graph theory for family of graphs of large Gers, but here it's everything is written in terms of dimension, not about cardinalities. And other important definition, let G be connected graph and G projective limit. And dA stands for the diameter of GI. In the case when diameter di is bounded above by C and I, because in the case of Gers bounded below, but here diameter, but not Gers, and we have upper bound, then we have algebraic approximation via small word graphs. It means in some sense the diameters of these graphs are the smallest possible. Small word term that actually came that our humankind with connection to person are know each other, yes? That relation is a small word graph. Diameter of this huge graph with millions of people is statistics show that 6 or 7 depends. So very small diameter. That's why we talking about small world. Our world is quite small. And connection with infinite network studies, actually in March of this year, it was a workshop on complex networks and fractals in Isaac Newton Institute in Cambridge. And I talk about the this large Gers approximation for trees and forests. Why it's important for people doing some stochastic processes? Because in probability theory, branching process is special stochastic process corresponding to random walk on regular forest, which can be infinite in many cases. And so forest is kind of deterministic part of branching process, which is of course very important, and we can work in normal way if, for instance, this forest defined in terms of algebraic geometry. Otherwise, with infinite sets, it's not. So, what that we have such definitions, and okay, we have just 3 direction, and about justification of this definition, because you see we can give a definition, but there is no object. It will be a shame, but in fact there are families of graphs, algebraic graph GI over commutative integrity ring K, which form a forest approximation of large Gers. And there are a family of algebraic graphs GI, which are form approximation of infinite tree. because forest, if we have connectedness of graph, a resulting graph will be connected, of course. So that's in case of small word graphs, we always obtain a tree. So in fact, what the first family of such graphs of large Gauss was obtained in 1995 in the work of myself, Felix Lazebnik, and Andrew Walder. It published in Bulletin of American Mathematical Society. After it was, in fact, originally defined over finite fields, but I changed it and defined the graphs over arbitrary commutative ring and integrity ring are especially important because these graphs can be used in symbolic for symbolic computation, and in symbolic computation the following integrity ring is important. We take integrity ring K and consider multivariable ring. We must have generators variables x1, x2, xn multivariable ring. This, of course, according to David Hilbert's statement, is integrity ring, and such a creature is very important in theory of symbolic computations. Okay, so I have some time, so that some reference here are given. Actually, some examples, because there are, which is not related with this definition above, famous family of Kelly graphs related to PSL2P XPQ, defined by Margulis and investigated by Lubotsky, Sarnak, and Phillips. They are families of large Gauss and families of small word graphs, but they are not approximations of tree or some infinite graphs, because graphs, groups PSL2P are simple and there is no homomorphism. So in this case, the projective limits are not defined, but this is an interesting side object. And today I will consider another problem, new problem, optimization problem for graphs. Actually, I will talk about algebraic graphs. So investigate cycle indicator of HV of vertex of K-regular graphs G, i.e. the minimal length of cycle through this vertex V. So for each vertex, we can consider totality of cycles through this vertex and get a minimum. And after we can define the cycle indicator of whole graph as the maximal value, because if I use here minimal, I obtain Gauss, but maximal value also reasonable because we have optimization minimax problem for graphs. And instantly from definition follows that this cycle indicator, that maximal value of cycle indicators for vertices is of course bigger or equal to the Gauss of the graph, which is minimal size of cycle graphs. So and again, similarly, we can change Gauss for consider a family of graphs with large Gauss indicators when HI are bounded by C log K minus 1 VI in case of finite graphs, and we can go to algebraic graphs and define family of homogeneous algebraic graphs such that here cycle indicator HI is constant on dimension of vertex set for GI. So the similarity between finite graph theory and algebraic graphs. And now I am ready to give you explicit construction. So we can consider for each integrity ring, which is important, the bipartite graph with points like kn, power of kn times. This is point set, and this is line set, kn, so we have bipartite graphs or incident structure. And point P1, P2, Pn is incidence to line L1, L2, Ln, if and only if the following relation holds. Difference of coordinates P2 minus L2 is L1, P1, P3 minus L3, P1, L2, P4 minus L4, L1, P3, P5 minus L5 here, misprint, P1 time L4, so we see alternating L1, P1, L1, P1, and so on. And we have here 1 plus 1 for this monomial term, and here is 2, and here we have index 2, 1 plus 2 is 3. So this is recursion is obvious, but in fact, behind this graph, the root system A1 with weight is standing. So they have algebraic connection. And actually, brackets and parentheses are used to distinguish points and lines. So here the theorem, maybe that let K be an integrity ring. Then for each odd n bigger or equal than 2, a cycle indicator of a graph I and K is at least 2n plus 1. So we have inequality that cycle indicator of n a k bigger or equal to n plus 1, which means that they form a family of graphs with large cycle indicator, and actually the constant C in definition here is the largest known. In for finite graphs we will get 2 log q minus 1, and if we have looking at algebraic graphs over a k may be real numbers or complex, so the constant in this definition is 2. And actually that is interesting result, and there are some conjecture connected with this. First conjecture, let F be a field with at least 3 elements, then for each odd n bigger or equal than 3, cycle indicator of graph A and F is in fact 2n plus 1. So the bound above is sharp, that this result is. And this first conjecture, and more strong conjecture, let G be K homogeneous algebraic graphs. Okay, this dimension of vertex set is K over field F with the vertex set V G with Gauss indicator H. Then we can consider class of such graphs and define over fixed field F and define function UHF H bigger or equal 6, this minimal codimension for variety of such graph. Codimension is just dimension of vertex set divided by this parameter K. That we can consider another function U from H, here no field F, so we can take minimal value via all possible fields. So that corollary from these conjectures, actually I think it's from the first one, that we have relation that UHF less or equal H minus 2 by 2, bigger or equal than UH. Right inside appears from the fact that Gers of this family A and F is to n plus 2. And this is a very applicable conjecture. It's some supporting statements are obtained. For instance, that let K be odd and P be the arithmetic progression of kind 1 plus n K plus 5 divided by 2, n equal 1, 2, and etc. Then for each integrity ring, F of prime characteristic P or 0, the cycle indicator ASF is exactly to S plus 2, where S is K plus 3 divided by 2. There is an integrity, an integer function n from K such that for all commutative integrity ring with unity, such that characteristic K is at least nk, the Gers indicator of the graph is 2s plus 1. Actually, from this supporting proposition, we already get, without any conjecture, that this function h from A, which doesn't depend from field F, less or equal than h minus 2 divided by 2. Okay, and final observation that it's interesting to look at homogeneous algebraic graphs over field F with even cycle indicator H of codimension H minus 2 divided by 2. We refer to them as cyclonic graphs. So example of cyclonic graphs. This class will contain geometries of all Chevalier group A2, F, B2, G2 together with graphs A and F for which Gers cycle indicator is exactly to n plus 2. This checked by computer for n less or equal 9 or bigger or equal 2, and there is theoretical result above that we have infinitely many fields for which we have such situation. So this interesting family, and there are interesting open question. You see, we can define cyclic gap for the graph with cycle indicator H as difference between H and the Gers of this graph. So in case of geometries A2, B2, G2, the cycle gap will be 0, H equals to Gers, but computer simulations show that in case of this graphs A and F, the cyclic gap is at least 2. But of course, it's interesting question just to prove this fact. Okay, I have just time for some remark that there are a lot of application of these graphs A and F to coding theory. About this topic today, Monica Polak will be speak. And there are application to construction of stream ciphers and post-quantum cryptography. So it will be talked by Timoteusz Chojecki today. And maybe I just go down and scroll because I have lots of information about these graphs and application to extremal graph theory, but I skip this. I will talk just about application. So here is my book, a new book, which is published by University of Curie Skłodowska this year. Graphs in terms of algebraic geometry, symbolic computation, and secure communication in post-quantum world. So that is connected. Previous my book actually also used graphs of large Gers. This advances in coding theory and cryptography. It's actually collective monographs. I am editor together with Tanush Shaska, V.C. Huffman from Chicago, and David Joyner from the Navy Academy of USA. I skip. I would like to leave some time for question. Thank you very much for your attention.